Hello everyone, today let's take a look at QP95 where we have a farm, 4 male cows and 6 female cows, and then 6 male pigs. So it's asking us how many female pigs must be present on the farm if sex and animal type are independent when selecting an animal at random. So when two events are independent, that means when you have information about one of the events, then it doesn't change the probability of the other event occurring. So if we let this be our sample space, and maybe first we break it up based on cows versus pigs, the animal type, well, we know that we have 10 total cows. We'll say 10 cows over here, and then we have 6 male pigs, but we don't know the number of female pigs, so we'll call the number of female pigs X. And then for our cows, we can partition them into 4 males and 6 females, obviously. Then in the pig section, we'd have 6 male pigs and X female pigs, we're saying. So when we're choosing a random animal and we know that the gender and the animal type are independent, well then look at how many equations that gives us that we can use to solve for this variable over here, the number of females. Because if these two events are independent, well the information that you're a cow does not change the probability that you're a male. The information that you're a pig also doesn't change the probability you're a male, right? The information you're a cow doesn't change the probability you're a female. The information you're a male doesn't change the probability that you are a pig. So you could have solved for this variable right here in a million different ways, right? You could have taken any one of these equations, or even the ones where the intersection is equal to the multiple of the individual probabilities when they're independent, right? And then when you just use one of these equations to solve for the number of female pigs, well then necessarily all of the other ones become true because this table only has 1 degree of freedom, basically. That's because we have a 2x2 contingency table with 1 unknown, so I'll go and draw that out later and we can talk about the degrees of freedom. But right now, let's just choose any single one of these random equations. I'm just going to blind fire. Let's go with this one. So this is equation saying when two events are independent, the probability that you're a pig, given that you're a male, is equal to the probability that you are a pig. So what's the overall probability that we are a pig? Well, there's going to be 6 plus X total pigs, and there's going to be 6 plus X plus 10 because of the 10 cows total animals, which is going to give us 16 plus X. Now the probability that we are a pig, given that we are a male, so first we restrict ourselves to only the males. There's 10 total males, and how many of them are pigs? Well, it's just going to be 6 of them, so we know that this is equal to 6 on 10. So when I multiply each side by 16 plus X and 10, I get on the left side 60 plus 10X, and on the right side I get 96 plus 6x, and then I subtract the 6x over here, I get 4x. I subtract the 60 to the other side, I get 36. So that tells me that x is equal to 9. So now let's do a sanity check. Does that make sense? Well, if I have 9 female pigs, now I know I have 9 females, and that also means that I have 15 total pigs, and now all of these equations will be true over here. Now the total probability that I am a pig is going to be 15 out of 25 total, which is going to give me 60%, right? Now the probability that I'm a pig, given that I'm a male, so I have 10 males and I have 6 pigs, is also 60%. The probability that I'm a pig, given that I am a female, is 9 out of 9 plus 6, so 9 out of 15, which is also 60%. Okay, so now I'm just going to blind fire the probability that I'm a male, given that I'm a pig. Okay, I'm a pig over here. The probability I'm a male is this right here, so 6 out of 15. So that's 40%. If I look in the cow section, the probability I'm a male, given I'm a cow, is 4 out of 10. So again, 40%. The probability that I'm a male overall is 6 plus 4, 10 out of 6 plus 9 plus 6 plus 4, which is 25. 10 out of 25 is also 40%. So all these equations over here are going to be true. You can check yourself. Also, the other equivalent definition of conditional probability, the probability of A intersection B, that's equal to the probability of A times the probability of B when two events are independent. So the probability that I'm both male and a cow, that should be equal to the probability that I am a male overall times the probability that I'm a cow overall. Also, say we were trying to solve for the number of pigs again. We were trying to solve for XF with this formula over here. How would we do it? So again, if I was solving for it this way, the probability that I'm a male would be I have 10 total males overall, 16 plus X total animals. And then here for my cows, well, I'd have 10 cows as well and 16 plus X total animals. Now the probability that you're both male and a cow, there's 4 total male cows out of 16 plus X, again, total animals. We could have canceled out a 16 plus X from each side, and we get 4 times 16 plus X, once we multiply the other one over, is equal to 100. And then we just get that 64 plus X equals, 64 plus 4X equals 100. And then again, you get that X equals 9. Okay, so anyways, my point was all that is that you could have solved for this in like a million different ways. I'm not going to go over them all, obviously. Now, the more interesting question is that how come when you figure out independence between one relationship, it just makes every single other one true as well? That's because in my contingency table, you can see over here, I have 1 degree of freedom. All that means is that when I fill in one of these unknown boxes, well, that makes all of the other ones have to be a certain value as well. So because there's only one free number in the 2x2 table, once you choose it such that one conditional ratio is satisfied, well, then all the other ratios must fall into the same overall ratio to keep the margins consistent, right? So for instance, for the cows, if I force the female to male ratio to be the same as, let's say, the ratio overall, well, then that automatically forces the female to male ratio in the pigs category to be the same as well. So yeah, sorry to go on a tangent there. I'll probably talk about degrees of freedom more when we do inference in the future, but this is the general idea. But that wasn't really the point to solving this equation. The point is there's like a million different ways to do it, and in every single way you should get that x is equal to 9 when you solve out an equation like this.